Hey there, this is Sally's Book Club. Tune in daily for curated global masterpieces. Today's featured book is Fermat's Last Theorem, subtitled The Epic Quest to Solve the World's Greatest Mathematical Problem. September 19th, 1994, might seem like an ordinary day to you, but for math prodigies, it marked the day they forever missed their chance. That's when mathematician Andrew Wiles completed the proof, an intellectual bombshell that rocked academia. Now, why did this 358-year-old puzzle captivate generations of brilliant minds? Mathematics permeates every scientific discipline, especially physics. From Newton's gravity to Einstein's relativity, equations became nature's language, driven by our thirst for truth. The author Simon Singh is a British Indian physicist. Dr. Singh directed BBC's award-winning documentary, Horizon, Fermat's Last Theorem. Though categorized as popular science, it focuses less on proofs and more on mathematicians' obsessive journeys. Listeners with middle school math can grasp 70%. High schoolers, 90% plus. Stay attentive. We'll explore this 230 kiloword masterpiece through 3 sections. Part 1, the origin story of Fermat's Last Theorem. Part 2, pre-breakthrough efforts by generations of mathematicians. Part 3, Wiles' ultimate solution to this ancient riddle. Let's begin with Part 1. Our story starts with Greek mathematicians Euclid and Diophantus. Around 300 BCE, Euclid wrote the 13-volume Elements. Later during the Ming Dynasty, Shu Guangqi translated it into Chinese. Centuries later, Diophantus wrote a mathematics treatise called Arithmetica. Mathematics is often described as the science of numbers and forms. While Elements deals with geometric forms, Arithmetica focuses on number theory. Originally also 13 volumes, only 6 survived Europe's medieval chaos. Despite being incomplete, these surviving volumes remain foundational in number theory. The French edition of Arithmetica holds special significance for our story. Now remember this French Arithmetica, its connection to Fermat's theorem will soon unfold. Let's meet our protagonist of this mathematical mystery. Pierre de Fermat's middle day denoted noble status. Born August 20th, 1601, in southwestern France to a prosperous merchant family. This privileged background ensured Fermat's excellent education. Following family expectations, he pursued civil service. Starting as local councillor, he rose to become regional chief justice, known for compassion and diligence, yet more passionate about mathematics than promotions. Later called the Prince of Amateurs, though some dispute amateur, given his achievements. His collaborations with Pascal established probability theory. Newton acknowledged Fermat's tangent method as precursor to calculus. His greatest contributions were in number theory, like discovering the second pair of amicable numbers. Amicable numbers, two numbers where each equals the sum of the other's proper divisors. The Pythagoreans found 220 and 284 minus 2020's divisors. 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, 100. Their sum equals 284, while 284's proper divisors sum to 220, minus considered lover numbers in ancient Greece. These were revered as guardians of love throughout Europe. A tradition emerged. Eating an apple engraved 220, while gifting one marked 284 to your beloved. A fruity version of love letters. 2 millennia later, Fermat discovered 17,296 and 18,416, the second pair of amicable numbers. This breakthrough cemented Fermat's reputation in number theory. Remarkably self-taught, his primary textbook being that French Arithmetica we mentioned. The edition featured generous page margins, perfect for annotations. Containing over 100 problems with solutions, it became Fermat's playground. He filled those margins with ingenious solutions and new theorems. 16th century French mathematicians loved intellectual showmanship. They boast conclusions but withhold proofs. a common practice. Fermat epitomized this, reveling in cryptic intellectual games. He'd taunt colleagues across Europe with claims like, "Can you prove this?" never sharing his methods. His margin notes contained conclusions with vague or missing proofs. Fermat died January 1665, taking many secrets to the grave. His secretive nature nearly erased mathematical breakthroughs. Fortunately, son Clement Samuel published his annotations. The 1767 publication, Diophantus Arithmetica, with Fermat's notes, contained 48 annotations. Annotation 2 became famous, written beside Pythagoras' theorem, known as Gugu theorem in China. A squared plus b squared equals c squared for right triangles. Pythagorean triples have infinite solutions like 3, 4, 5 or 5, 12, 13. Note, 6, 8, 10 is just scale from 3, 4, 5. For not replace the exponent 2 with 3, then 4 minus neither yielded valid solutions. He famously wrote, "It's impossible to separate a cube into two cubes or a fourth power into two fourth powers, and, or generally any power higher than the second, into two like powers." Thus, Fermat's last theorem was born. We'll call x to the power of n plus y to the power of n equals z to the power of n, the Fermat equation where n greater than 2. His teasing remark, "I have a marvelous proof, but this margin is too narrow to contain it." This annotation dates around 1637. No historical records show Fermat ever demonstrated this proof. All his other claims were subsequently proven, except this one. This theorem remained unproven until 1994. Hence, Fermat's last theorem. Now we'll explore how this enigma captivated brilliant minds. Part 2. First breakthrough came from Leonhard Euler, the Swiss polymath who solved any problem. His work spans multiple mathematical disciplines. True test, anyone claiming math knowledge but ignorant of Euler is a phony. About 90 years after Fermat's death, Euler took up the challenge. His strategy: prove specific exponents first, like 3 or 4, then generalize. Typical Euler brilliance. From Fermat's notes, Euler discovered a hidden proof for exponent 4 using infinite descent. This complex proof by contradiction won't be detailed here. In 1753, Euler wrote to Goldbach, claiming proof for exponent 3 using similar methods. Though promising, Euler failed to generalize these proofs. The most prolific mathematician met his match with this theorem. Fermat's n equals 4 proof extended to multiples like 8, 12, 16. Euler's n equals 3 worked for 6, 9, 12, reducing the problem's scope. Thus, only prime exponents 5, 7, 11, 13, and so on remained unproven. Quantum leap in approach, though methodologically derivative. Were women completely absent from this mathematical arena? Mathematics proved unforgiving for women seeking recognition. Enter Sophie Germain, French heroine of number theory. Born 1776, she faced locked doors at École Polytechnique, founded 1794. And student Monsieur Leblanc left Paris. Opportunity arose. The school unknowingly sent course materials to his vacant address. Germain seized the chance, adopting Leblanc's identity. Professor Lagrange noticed dramatic improvement in Leblanc's work. Demanding meeting his star pupil, Lagrange uncovered the ruse. To his credit, Lagrange became Germain's mentor, though Lagrange's expertise lay beyond number theory. Germain decided to correspond with Gauss, the prince of mathematicians, versus Fermat's prince of amateurs. She maintained her Monsieur Leblanc pseudonym in their correspondence. Germain defined a class of primes now bearing her name. A Germain prime P satisfies both P and 2P plus 1 are prime numbers, she proved. If n is a German prime, any Fermat equation solution must have a multiple of n. This strongly suggested Fermat's equation had no solutions. Gauss replied, "Arithmetic has found in you its most able friend." Without knowing her true identity, Germain began this correspondence at 20, a mathematical prodigy in skirts. Though her direct contributions stopped here, others built on her work. Dirichlet and Lamé proved cases for exponents 5 and 7 using Germain's methods. 5 was German prime, 7 not, requiring method refinement. Progress summary. Exponents 3, 4 multiples, and primes 5, 7 proven. Then came a century-long mathematical drought. The French Academy offered 3,000 francs, massive incentive. Mathematicians raced for both glory and the purse. Augustin Louis Cauchy, of calculus fame, joined the fray. Cauchy versus Lamé, academic duel of the century. 3 weeks post-announcement, both deposited sealed proofs at the Academy. Priority disputes loomed. Academic sprint began. After months, their competing proofs flooded Academy publications. May 24th, 1847 became a day of reckoning for Lamé and Cauchy. German mathematician Kummer sent an academic bombshell to the Academy. His letter exposed fundamental flaws in both mathematicians' proofs. Kummer declared, "Your approaches can never prove Fermat's theorem." As number theory authority, Kummer's verdict carried significant weight. This epistolary strike devastated all working on the theorem. Researchers vanished like morning mist, Lamé and Cauchy included. Despite criticism, Cauchy surprisingly thanked Kummer. In 1875, he proposed awarding Kummer the original prize money. Enter Paul Wolfskill, 1908's mathematical patron saint. This German industrialist will established 100,000 mark reward. Legend says heartbreak drove Wolfskill's dramatic gesture. After romantic rejection, he planned meticulous suicide. Final letters written, affairs settled, midnight gunshot planned. With hours remaining, he idly read Kummer's critique. Kummer's analysis of failed French proofs became his bedtime reading. Suddenly, an unverified assumption leaped from the text. Wolfskill realized, disprove this assumption, revive the proof. Dawn found him alive, mathematical salvation complete. The would-be suicide became mathematics' accidental patron. Kummer's small gap closed, but Fermat's theorem remained. Wolfskill, thrilled by his discovery, found renewed zest for life. He shredded farewell letters and established a prize fund for the theorem's proof. Thus, Fermat's theorem earned its nickname, the life-saving theorem. The 100,000 mark reward proved irresistible. First year, 621 proofs flooded academic journals. By second year, publishers refused announcements, overwhelmed by submissions. Mainstream mathematicians grew skeptical, providing counter-arguments instead of solutions. By 1931, doubts emerged about the theorem's probability. Gödel's incompleteness theorems suggested possible unprovability. Cohen's 1960s method finally confirmed its decidability. Our protagonist finally enters. Andrew Wiles, born 1953 in England. At 10, Wiles encountered E.T. Bell's The Last Problem, detailing Fermat's theorem. It looked simple enough for a child, yet eluded giants, Wiles recalled decades later. The problem's deceptive simplicity captivated him permanently. 1973, graduated from Merton College, Oxford with mathematics degree. Began postgraduate studies at Cambridge's Clare College under John Coates. Coates discouraged Wiles from Fermat. Impossible for a novice researcher. Coates directed Wiles towards elliptic curves, the crucial turning point. Wiles' focus. Integer solutions in elliptic equations, their existence and quantity. Superficially unrelated to Fermat's theorem, but connections ran deep. Our story splits to post-war Japan's economic revival, mid-1950s. Two mathematical prodigies emerge, Tanyama and Shimura. Their university meeting forged an unlikely partnership. Shimura's eccentric personality, traditional dawn-rising workaholic. Taniyama, disheveled genius who slept till noon, much to Shimura's envy. Taniyama possessed the gift of productive error, missteps leading to truth. Shimura's failed attempts to replicate this talent, their obsession, modular forms, 19th century mathematical constructs. These forms combine translation, rotation, and reflection symmetries. Elliptic equations versus modular forms. Seemingly separate worlds. 1955 Tokyo Symposium. 36 problems presented, including Taniyama's 4. Tanyama's fourth question proposed their revolutionary correspondence, thus born Taniyama-Shimura conjecture, initially dismissed, then recognized as profound interdisciplinary bridge. Mathematical heavyweights endorsed the conjecture's potential. Papers proliferated. If Taniyama-Shimura holds, then enter phrase 1984 insight, linking Fermat's equation to elliptic curves. Frey posited, proved Taniyama-Shimura, and Fermat's last theorem falls. Wiles, now established at Princeton, felt the mathematical call to arms. Summer 1986 marked his solitary crusade's beginning. He entered monastic research, no collaborators, no leaks. Fear drove this secrecy, both of failure and intellectual theft. All non-Fermat projects abandoned, only wife Nada knew the truth. March 8, 1988. The New York Times nearly shattered his dreams. Miyake's claimed proof using differential geometry briefly crushed him. The flawed proof's collapse reignited Wiles' determination. 18 months mastering modular forms and elliptic curves. By late 1988, mathematical induction became his chosen weapon. Early progress flowed smoothly, until 1991's roadblock. Desperate, he attended a UK elliptic curves conference. Dual purpose, seek inspiration and mental respite. There, Coates mentioned the Kohlhagen method casually. A graduate student's project became Wiles' lifeline. Months mastering algebraic components he'd overlooked. Finally swallowing pride, he confided in colleague Nick Katz. May 1993. Collaborative breakthrough with Katz. Cambridge June conference chosen for the grand reveal. Poetic justice. Coates organized the historic session. Wiles requested 3 lecture slots. Coates surrendered his own, enabling the historic trilogy. First lecture hinted at Taniyama-Shimura direction without full disclosure. The final breakthrough remained tightly guarded. Second presentation maintained deliberate vagueness. The elegance will reveal itself tomorrow. Wiles' tantalizing cliffhanger. Day 3, champagne chilled as he uttered, "I think I'll stop here." 2-month scrutiny period began, per Wolfskell's stipulations. Submission to Inventiones Mathematicae initiated rigorous peer review. Katz-Lucy's meticulous examination uncovered subtle flaws. August 1993, critical error emerged, met with ominous silence. By December, media declared another false alarm. April 3, 1994, emails proclaimed, "Stunning counterexample found." Noam Kaiser's alleged disproof echoed his prior Euler conjecture work. Wiles froze, terrified to verify the April Fool's prank. The mathematical community collectively facepalmed at the hoax. 14 desperate months yielded no progress. September 19, 1994. Wiles' final review of his proof commenced. Suddenly, the abandoned Kohlhagen method resurfaced as salvation. Euphoric breakthrough, the missing piece clicked into place. Next morning's verification confirmed it. Absolute certainty by 11 a.m. Nada's impending birthday became symbolic deadline fulfillment. The long-promised birthday gift finally materialized. May 1995, 130-page definitive proof published in Inventiones. 8 years obsession left simultaneous relief and emptiness. No replacement for childhood love, though new challenges await. Mathematics siren song. Nothing rivals Fermat's allure. 358-year saga. Human intellect's triumph through struggle. Modern mathematical conquests share innovative methodologies. Hurlman's 2003 Poincaré proof via Ricci flow revolutionized topology. Zhang's 2014 twin prime breakthrough validated interdisciplinary approaches. Mathematical unification vision manifests through these triumphs. Each breakthrough expands humanity's explanatory lexicon. This concludes our journey through Fermat's last theorem. Full notes below. Until tomorrow.